11, 10, 9,
8, 7,
6, 5, 4,
3, 2, 1, 0. Ignition.
50 years after Neil Armstrong stepped on the moon, a new space race is gripping humanity's imagination. The distant goal is now Mars, the red planet. However, the big state players are no longer alone. Private companies have invested hundreds of millions to be a part of the race to Mars and stake their claim to the multi-billion-dollar space industry back on Earth. December the 5th, 2014. For the first time in 40 years, the United States is launching a newly designed capsule for human spaceflight. This is the first test flight of the Orion space capsule, designed to become the standard vehicle for human exploration of deep space.
5, 4, 3, 2, 1. And liftoff at dawn, the dawn of Orion and a new era of American space exploration.
The American-built Orion capsule is designed to fly through space attached to a European service module providing life support and propulsion. The world's most powerful rocket will kick the spaceship into its deep space trajectory, and what is left of it will return to Earth's atmosphere. While still at the forefront of space exploration, NASA is no longer alone in the race to the red planet. Aside from the pure pursuit of scientific knowledge, there is also a strong profit motive driving the new push to explore Mars. Private company SpaceX is already employing its space capsule, Dragon, to resupply the International Space Station. And when in February 2018, Elon Musk's Falcon Heavy launched the entrepreneur's own Tesla sports car onto a course for Mars, it wasn't just a brilliant PR stunt, but also a long-term investment in space.
The most challenging test of Falcon Heavy was nothing to do with putting a Tesla on the route to Mars. It was to fly a trajectory that for 6 hours loitered in the Van Allen belts.
Doing Mars landing is one of the scariest things that I believe that we do.
It's the big step, the International Space Station, a huge worldwide project running with JAXA, with the European Space Agency, with the Russians and NASA. And now we continue. We go the next giant step in direction of Moon Mars. And that's what we do again jointly. And only in this, let's say, joint team effort, we can be successful.
The first step to interplanetary travel was getting to the moon, which the United States and Soviet Union began working on in the 1960s, culminating with the first moonwalk in 1969.
It's one small step for man, one giant leap for mankind.
Mars exploration has been underway for decades, using orbiters, probes, and rovers. Mapping began in the early 1980s, but new imaging and information technology on the rovers and satellites has brought back hundreds of thousands of high-resolution photos, allowing for detailed 3D mapping of the Martian landscape. Building the rovers and landing them on Mars is the task of the Jet Propulsion Laboratory in Pasadena, California.
An ancient old question is, are we alone? Or are there life in other parts of the universe outside Earth? And Mars is an obvious place that we should look. Question is, did Mars have the habitable environment that I mentioned? And if it did life arise? If not, why not?
The Curiosity rover that successfully landed in a low crater on Mars called the Gale crater in 2013 is given commands from Earth by research geologist Lauren Edgar, here at the USGS Astrogeology Space Center in Flagstaff, Arizona.
One of the first pictures that we got was from the front hazard camera, so that's located on the chest of the rover, kind of looking at the foreground. And the sun was behind us, it was setting at the time. And so you could see kind of the shadow of the rover extending in front of us. And in the distance, you could see Mount Sharp, this big mountain that we had gone there to explore. So it's kind of a good perspective of this is where we are, you could see the shadow of the rover, and you could see where we were trying to get to.
We were able to show that that environment in the ancient past is very, very likely habitable. And that is a major milestone for our program. You know, we've been looking for the day to show that Mars was indeed at one time have that setting that was conducive to the emergence of or sustaining of life. We are also in the process of trying to understand what is Gale Crater, what made it that way.
The voyage to the Red Planet is fraught with immense risk. Earth and Mars rotate around the Sun at different speeds round different orbits. But even at their closest, which is every 26 months, they are 55 million kilometers away from each other. Using the technology available today, astronauts traveling to Mars face up to 9 months confinement in a small vehicle exposed to dangerous radiation from the Sun and cosmic rays. A global community of scientists and engineers is in the process of planning the first human voyage to gain first-hand insight into the geology of Mars. The editor of Spaceflight magazine, David Baker, has tracked the evolution of space exploration over 4 decades.
Well, Mars has gripped the human imagination for centuries. It's a very distinctive red object in the night sky, and it seems to have been entrenched in mythology and stories that civilizations have been attracted to and created over millennia. And really, since the advent of science fiction in the late 19th century, speculation began as astronomy increased to the point where it was possible to speculate on the atmosphere of Mars, that this is a world that could support life.
Since the last Apollo mission in 1972, the furthest humans have gone into space has been the low Earth orbit of the International Space Station, continuously occupied since the first crews arrived in 2000. For nearly 20 years, humans have conducted experiments aboard the space station, which lies outside the atmosphere but within the Earth's protective magnetosphere. While the magnetosphere acts as a precious shield against the sun's radiation, it is also a trap for highly energized atomic particles that form 2 wide donut-shaped belts around our planet. These belts, called the Van Allen belts, are an especially dangerous place for humans.
And Earth is like a giant bar magnet of iron, because it has iron in its core. And so, like a magnet, it attracts all these radioactive particles that form the Van Allen radiation belts, and that's known as the magnetosphere. And it has a long tail on the opposite side from the sun, which stretches all the way out as far as the distance of the moon and beyond.
Over 2 decades, contributions from the USA, Germany, Italy, Japan, Canada, and of course Russia have turned the space station into a global village in the sky. It is only logical that the next giant steps outside the Earth's magnetosphere and beyond the Van Allen belts also be coordinated internationally.
As we go forward beyond the International Space Station, it really is going to take an international effort. There's no single country that can afford even the next step of a deep space gateway or operations around the moon, let alone to Mars. No single company, certainly not a government on its own, can mount this unless it was a major program involving an unacceptable quantity of government funding.
But with the ISS slated for retirement in 2028, the international space community is now making bold plans for the next phase of human spaceflight. Mars is the goal, but getting a new space station deeper out in space as a stepping stone is key. Unlike the ISS, the proposed Deep Space Gateway, sometimes called the Lunar Orbiter Platform, will orbit the Moon rather than Earth. Astronauts will be 1,000 times more distant from Earth than the ISS, no less than 400,000 kilometers from home. This new station, located outside the Earth's protective magnetic field, is being conceptualized and engineered in centers all over the world. Building the Deep Space Gateway and going beyond it to Mars will require massive rockets able to lift at least 20 tons of hardware, including the crew capsule, the service module, and any living quarters. While from the ISS, Earth is clearly visible through the station's cupola, astronauts on the Deep Space Gateway will see Earth as just a spot, the size of a thumbnail held at arm's length. They will be much more vulnerable to radiation in the high-energy cosmic rays. Help will be weeks away. And yet, it is still considered a safer option than flying directly to Mars.
The Deep Space Gateway, as it's called, would be a space station-like group of modules in orbit around the Moon. And it would be serviced potentially by commercial cargo lifters, much as those that now supply the International Space Station, plying back and forth once the space agencies, NASA, the European Space Agency, Roscosmos in Russia, Japan, JAXA, and the Canadian National Space Agency. And maybe China at some point will come aboard on this. But it is a program that is a consensus to create an environment like the International Space Station. So think of it as a mini space station in orbit around the Moon.
NASA's new manned spacecraft is called Orion, which is a capsule and service module combination. The European Space Agency is providing the service module, which is being made by Airbus in Germany. NASA, meanwhile, contracted with the American aerospace and defense technology giant Lockheed Martin to build the crew capsule and the Space Launch System, billed as the biggest rocket ever made. Tim Chihan is the lead space exploration architect at Lockheed Martin's Space Systems facility in Denver, Colorado.
After the retirement of the space shuttle and the successful missions of the International Space Station, the next step for NASA is to further explore deep space. First the Moon, and then going on to Mars. So Orion, the spacecraft, and the Space Launch System, the launch vehicle, has been designed to take 4 crew to do missions at the Moon and beyond. Orion and the Space Launch System, SLS, are NASA's vehicles for taking crews back into deep space.
To keep the Orion spacecraft light, the external shell is made of aluminium-lithium alloy. To protect the capsule upon re-entry to the atmosphere, it has a heat shield made of Avcoat, developed for the Apollo missions.
Orion is composed of a few different modules, and starting from the bottom, there's the adapter between Orion and the launch vehicle. Then there's the service module. The service module of Orion provides propulsion, provides electrical power, provides gases and fluids for the life support system. The service module mass is 15 metric tons, and 9 metric tons of that mass is propellant. The Orion crew module at its widest point on the heat shield is about 5.5 meters wide, and the habitable volume inside the crew module is about 9 meters cubed.
There are 5 mock-ups that have been used for testing the different phases of the mission, including one for pilot training at NASA's Johnson Space Center in Houston, Texas.
And then we get into the crew module itself, where the crew sits. That includes, again, another propulsion system for when they're re-entering the atmosphere. Includes the heat shield on the bottom of the capsule, as well as the thermal protection systems around the back of the capsule. There's computers in there, all of the life support systems, seats, displays and controls, safety equipment like a life raft, and anything else needed to keep the crew alive. And then at the very top of the capsule, in the forward bay, is where all of the parachutes are for landing. And then what sits on top of the crew module for launch is the launch abort system, which can pull the crew module away from the launch vehicle in case of any problems.
Its controls are based on the touchscreen technology already being used in the Boeing 787.
So the Orion avionics and displays and controls are an evolution of commercial capabilities like in the 787 Dreamliner. So unlike the space shuttle, which had switches all over the place and behind your head, there's a very few switches on Orion, and they're all very safety critical switches. But the glass cockpit displays and the cursor control devices and joysticks allow the crew to have quite a bit of flexibility in how they command and control Orion.
NASA's Orion crew capsule will be attached to a service module being built in Europe. The skeleton of the module is being manufactured in Turin, Italy. It will then be finished at the Airbus facility in Bremen, Germany. Airbus engineers are basing the module on a tried and tested concept: the automatic transport vehicle used to resupply the International Space Station. Matthias Gronowski is the European Space Module Program Director.
The European Service Module, as part of the Orion spacecraft, there's a certain technology which we are reusing and which has been derived from ATV, from the automated transport vehicle. So what we see here is certain portion is continue life in that new spacecraft.
The basic structure of the European Service Module is built at the Thales Alenia Space Facility in Turin, northern Italy. The head of human spaceflight is Franco Fenoglio, a veteran of space engineering.
What we are doing for the European Service Module, we are basically doing the entire thermomechanical part, so the structure. And the structure, this is, I would say, more closer to a satellite structure than a module, because it's an unpressurized structure. So it's made by aluminum part, but also with a carbon fiber part, in particular an internal panel.
What we supply with the European Service Module is we supply power to the entire spacecraft via our solar array wings. So here it's 11 kilowatt, for example, just to give you a number, we're generating for the entire vehicle. Out of the 11 kilowatt, there will be the big portion transferred to the crew module. We are delivering basically the air condition in both directions, heat and cold side.
Another pretty large part is the thermal control, which is an active thermal control. That means with pumped fluid loop, and so in the external part, the heat is rejected via thermal radiators, and so mostly the entire surface of the service module is covered by body-mounted radiator.
And last but not least, we fly crew. And if you fly crew, it's important that you have water and you have all your consumables on that spacecraft. So here we need to generate the atmosphere basically in the capsule.
And the other part that we are doing also here is the so-called consumable system that include all the system for the provision of water, and gases to the capsule.
After being launched by the world's biggest rocket, the capsule and service module unit will be propelled into the desired orbit by a smaller onboard rocket fueled with hydrazine.
So the propulsion subsystem of the European service module consists of 33 thrusters, motors in general. So there's one big motor which is a reuse from a former shuttle heritage or former shuttle area. That's a so-called orbital maneuver engine. So that's an engine which has been flown in this specific case more than 10 times.
The Orion capsule and service module unit will have its own power thrusters to control its trajectory. The pushing power is measured by the Newton, equivalent to the gravitational force on a 100-gram weight. A kilonewton is 1,000 times greater.
The main thruster is generating 27 kilonewton, and then we have several others. So the reaction control thrusters are 200 Newton thrusters, and then we have the 400 Newton thrusters. Those are the auxiliary, which are serving as backup. In case the main engine fails by ignition, then we are still able to bring the crew home safely by our auxiliary thrusters. The propellant we are flying is more an MMH. That's very specific configuration. We are flying here on that spacecraft on all the thrusters the same configuration, the same level of and same type of propellant.
Like all the other elements of the propulsion system, the European service module will be destroyed on re-entry into the Earth's atmosphere. But NASA and the European Space Agency plan to make deep space flight a regular event.
This portion of our contribution into the entire spacecraft will burn in the atmosphere, and by that the entire hardware is gone. But we are working on the second European service module, currently in Torino at Thales Alenia Space. So there the primary structure and the secondary structure, I guess, is being assembled.
So the next mission for Orion, Exploration Mission 1, is an uncrewed test flight of Orion out into deep space. The vehicle will go further than any human-rated spacecraft has ever gone, further than an Apollo spacecraft, and go into a high orbit around the moon for 25 to 40 days to test out all of its systems in deep space before we fly with crew. And then it will come home and re-enter and land and be recovered by the Navy. The next mission for Orion, Exploration Mission 2, will be the first crewed flight of Orion. They will be launched into a high orbit around Earth, check out all their systems, and then do a flyby around the moon and land back at Earth.
The Orion spaceship will be launched in December 2019, atop the Space Launch System rocket on an unmanned test mission. The following year, the system will be tested with 4 astronauts aboard. They will go beyond the moon. It is estimated they will spend 3 weeks in the cramped space before returning to Earth. Once the first manned flight of NASA's Orion spaceship has been completed successfully, then the voyage to the moon-orbiting Deep Space Gateway can proceed, paving the way for the mission to Mars. But in the race to the red planet, will private companies get there first? And what is motivating them?
Elon Musk in 2017 launched 18 satellites, more than any other operator in the world. And he's doing so at a cost. The average cost of one of those Falcon 9s is about $90 million. That's compared to $180 to $220 million for the conventional other rockets like Ariane and the Deltas and the Atlases, which have been used by the big mega corporations that have held a monopoly for decades.
High-tech startups like Elon Musk's SpaceX and Jeff Bezos's Blue Origin have slashed the cost of spaceflight by building reusable rockets, ones that simply return to the launch pad once used.
The exciting flight of Falcon Heavy, Elon Musk's SpaceX, that cost just under $600 $600 million directly out of Elon Musk's bank account, because this is not a public company, it is a private company, and he put his own money into that. NASA estimates it would have cost the American government $4 billion to do what Elon Musk did with $600 million in Falcon Heavy.
February the 6th, 2018. The SpaceX Falcon Heavy shoots into space, powered by 27 Merlin cryogenic engines. It was Elon Musk's first step on the path to Mars and a public relations masterstroke. Elon Musk's Falcon Heavy wasn't only the largest rocket in the world, but its avionics package was put to the test for 6 hours in the highly disruptive and dangerous Van Allen belts.
Elon Musk knew that nobody was providing a capability that was a unique niche of what is a classified requirement from the National Reconnaissance Office and the US Defense Department for a satellite carrier that can loiter in the Van Allen radiation belts. And the most challenging test of Falcon Heavy was to fly a trajectory that for 6 hours loitered in the Van Allen belts. And the very, very survival of the avionics, especially beefed up for that unique, never before achieved capability, was what Elon Musk is going for, because he's offering to fly these national security payloads at a quarter the price of the big boys like United Launch Alliance, the convergence of Boeing and Lockheed Martin.
Getting all the way to the Red Planet will involve traveling through space for months. Astronauts will need a habitat during the voyage to deep space, a concept both Thales Alenia and Lockheed Martin are developing.
But right now, Lockheed Martin has study contracts from NASA to determine the design of the Lunar Gateway. And the Lunar Gateway is expected to have a few different modules, a power and propulsion element that provides electrical power, propulsion capability, consumables, communications, and a habitat where the astronauts will live and work, starting with missions of 30 days. And right now I'm sitting in Lockheed Martin's mock-up of the habitat design.
With this vehicle we are currently building, we can put on top a habitat with about 10 metric ton. That was something we can fly with our vehicle, at least in direction to the moon. If we would go to Mars, of course, we need to put something more on top, especially in terms of the propulsion system. But a habitat, that's what we are working currently on.
Most of these elements of the cislunar infrastructure will have to be launched in the new space launch system of NASA, but co-manifested with Orion. That means that the mass target at launch of the payload, in this case, which is the module or the logistic cargo, etc., is reduced. So one of the key challenges is definitely the mass optimization.
The pressurized Cygnus logistics module has already been used 8 times to deliver food and supplies to the International Space Station. Building on that experience, Thales Alenia Space is now adapting the module for use as a potential habitat for astronauts in deep space. Here in the Turin plant, the company uses friction welding to bond the components together seamlessly.
All these cislunar mission will be served in terms of crew transport by Orion. Orion is a capsule that has some habitability capability inside, but the first idea for Cygnus is to use it such that it can dock to Orion and actually represent a sort of augmentation of the volume for the crew, together with the augmentation of also stowage capability, and providing maybe some sharing of functionality between Orion and Cygnus.
Making the voyage into deep space safe and comfortable is only a fraction of the massive task facing scientists and engineers plotting the course to Mars. NASA's moon missions between 1969 and 1972 marked the only time in history that humans left the Earth's protective magnetic shield and ventured beyond the Van Allen belts. Back then, they were launched into space by massive Saturn V rockets, which were cryogenic. Today, with heavier payloads, more power is needed. That extra power to get out of the atmosphere is provided by lateral solid fuel boosters.
Hydrogen and oxygen, when it's as a gas, it's 30 to 40 times the volume it has when it's a liquid. So because a rocket must be contained within a reasonable size, you want to shrink those propellants down, and therefore you've got to liquefy them. A rocket motor is a heat engine. You bring propellants in to a chamber which has an exhaust outlet. You burn them in the chamber and they liberate all that energy out through the nozzle.
For long missions in deep space, whether at the moon or at Mars, the logistics supply chain is an important consideration, particularly for propellant, which makes up a huge proportion of any space vehicle's mass. So we're looking at concepts of how to deliver propellant. And because hydrogen and oxygen is a very efficient propellant mixture and can be made from water, which is found throughout the solar system, we feel that a water-based economy being set up in deep space may be an enabler for deep space exploration. And the idea is that commercial providers would obtain water from in-space sources, or maybe just from the surface of the Earth, and deliver it to be turned into hydrogen and oxygen propellant.
Carrying liquid propellants, such as hydrazine, increases the weight of space vehicles considerably. One alternative under consideration is electric power, generated by solar panels.
Electrical propulsion system is part of our, let's say, portfolio. We implement that on satellites already. For Bremen, for the human spaceflight, for the time being, it's not part, but it will become, because that's the next step on this specific area, propulsion systems.
For cargo deliveries, solar electric propulsion, which uses electrical power from solar arrays to accelerate propellant, is a key technology. It provides very high efficiency, although very low thrust. So those cargo delivery missions would take on the order of a number of years, and that's not as great for using for crew transportation.
A new form of propulsion is under development that uses charged particles called ions to provide thrust. The first ion engines are already available.
Electric propulsion is that it is really the possibility of using a propulsion system which can keep going for weeks and months at a time and doesn't rely on conventional fuels, but essentially produces a stream of ions, and that can be provided either by solar arrays which gather electrical power from solar and convert it into a stream of ions. The other way is that you could use a small nuclear reactor.
We don't think that going to Mars requires some major breakthrough in propulsion technologies. We have the technologies today to get to Mars and back. And sure, someday if we've got nuclear thermal rockets and other interesting new developments, we'll incorporate them into architectures, but they're not necessary.
Lockheed Martin is also developing the Mars Base Camp concept, taking the Deep Space Gateway one step further.
Mars Base Camp is Lockheed Martin's vision for sending crew to Mars within about a decade. Building upon what we've learned with Orion and what we'll learn with the Lunar Gateway, it's a system that includes habitat elements, propulsion elements, large solar arrays, laboratories, to be able to go on the 3-year round trip to Mars orbit and back. Later on follow-on missions to Mars, we also have a concept for a single-stage refuelable lander and ascent vehicle that would operate out of the orbiting Mars base camp and visit the surface of Mars with crew.
NASA's Jet Propulsion Laboratory in Pasadena, California, is responsible for engineering and launching the rovers. Phuc Le is the head of the Mars program and oversaw the landing of 2 rovers on the red planet's surface.
We have sent 3 orbiter spacecraft from NASA, and we have sent 4 landed missions from NASA. And over this new era of exploration, we learn a lot more about Mars, how complex it is, how diverse it is. We have found very strong evidence of the presence of liquid water, again, in the ancient parts of Mars. And with Curiosity that landed about 5 years ago, one of the key questions we've been asking, in fact, probably the main driver of our robotic exploration is, was there life possible on Mars, either in the past or perhaps even today?
So if we do send future humans to Mars, we'd probably be looking at habitats that would be underground or built into a hillside so that you're partially protected from that cosmic radiation. You know, having any of the necessary resources. There are some places on Mars that might have some water, you know, as subsurface ice, but right now those aren't places on Mars that we can easily land a spacecraft.
The European Space Agency is also interested in landing a rover on Mars. Close to the windswept dunes of Noordwijk in the Netherlands, the ExoMars project is specifically designed to search for signs of life on the planet. In 2016, the first ExoMars expedition was supposed to send a lander onto the Mars surface while aerobraking a massive orbiting satellite. Albert Haldeman is the European Space Agency payload manager.
The Trace Gas Orbiter TGO is the biggest spacecraft ever launched to Mars. And that's just by itself. It also had a 600 kilogram entry, descent, and landing demonstrator module on top of it when it launched. And it delivered that to Mars. It released the EDM Schiaparelli before it itself did its Mars orbit insertion. And then in the last year, TGO has been aerobraking down to its science orbit.
Unfortunately, software errors in the lander's computer guidance system caused it to crash into the Mars surface. It taught scientists a lot about the Martian atmosphere and the physics of descent.
We will take the lessons from the Schiaparelli lander that didn't succeed fully, but we got the data. In fact, we got telemetry all the way down to the ground, such as it is. And we are using that to make changes to the design we had for the lander that will carry the rover on its back.
The reasons that landing on Mars is so hard and kind of dangerous is when we enter the Martian atmosphere for Curiosity, the kinetic energy of that capsule is roughly equal to the kinetic energy that I once calculated, roughly equal to 18,000 Formula One race cars at high speed. So they're going around, as you know, the Formula One people go around at 200 miles an hour, and there are 18,000 of them. And by the time the entry, descent, landing process is finished, we have to land very gently onto the surface of Mars with the equivalent energy of a person riding on a bike.
The problem of landing actually on the surface of Mars is that there's very little help from the atmosphere because it's so thin. So parachutes need to be deployed at supersonic speed and slow down the vehicle initially as it begins to come from Mars orbit down, curving down toward the surface. Retro rockets are essential because there's no other way for terminal braking to land at a safe speed for the survival of the crew. Landing very, very big vehicles on the surface of Mars, such as that would be required for carrying people, is very problematic indeed.
This would be one of the most difficult moments of the whole mission. Between 2018 and 2020, 3 new space missions are planned with monster rockets before humans will actually go to Mars. The first launch of the SLS with an unmanned Orion capsule is due for 2019. It will be the first time a rocket has taken a capsule into deep space since 1972.
Before we put humans down on Mars, there's going to have to be several, I would suggest at least half a dozen demonstration attempts through various levels of the atmosphere. The pressure on Mars is different in summer compared to winter in that hemisphere you're coming down upon. It's different at altitude versus low altitude. One of the site selection criteria is to go, while satisfying all the scientific criteria, for the lowest possible altitude of the terrain on which you're landing to get the best bite into the densest level of atmosphere, because it pools like a fog.
If a manned mission to Mars is successful in the next decade, when the astronauts reach the Martian surface, they will see the multiple rovers sent to scout the planet first.
One of the goals of this mission was to identify habitable environments, and I think we've been successful in doing that. Obviously, it would be great to find some evidence of life, but this instrument, these instruments on this mission weren't necessarily designed to do that. So one can hope, but in the meantime, it's really fun seeing all these familiar environments present on this planet, and thinking about what it would be like to be sitting on the shores of this big lake in Gale.
Curiosity has moved over rugged terrain to reach the crest of Gale Crater. Its path has taken it over rock and sand, which it has sampled and tested. Though designed to last under a year, Curiosity is still making new discoveries more than 5 years later. NASA spends billions of public monies on space exploration, but the private contractors working in the space industry pay back over and above that in taxes.
The global space budget is worth nearly $400 billion a year. Now, 78% of that is in the hands of commercial, private or shareholder invested organizations. And the interesting thing is that the United States, NASA, spends more than half the world's total expenditure on civilian space operations. And all of that government money is less than the amount of tax that is collected from the other 78% of commercial endeavors. So American taxpayer, European taxpayer, wherever you are actually, as a taxpayer, getting a return rather than a net outflow.
Space exploration is not just about the thrill of discovery, however. The engineering and innovation breakthroughs from past space research have made a difference here on Earth. The mission to deep space and then to Mars is no different.
From what began as a space race has come a series of programs that benefits everybody on Earth. We know of the benefits from weather satellites. We know of the benefits from resource monitoring to inform us of how appalling is our husbandry of this Earth, on which we have huge responsibilities. Of the existence of an ozone layer, that we could work to legislate against fluorocarbons that were eroding it. Of the ability to put satellites into space that will help us put rescue teams with those in harm's way, stranded on fog-bound mountainsides.
Already, space research is helping scientists understand more about medical disorders such as bone density loss, but also about farming in arid lands, water saving, recycling and sustainable technologies, not to mention the evolution of our own planet. Today, robotics is so far advanced that by 2020, humanoids will be able to perform so many tasks, it may be unnecessary for men and women to risk their lives on the red planet. For decades, robots have traveled over the surface of Mars, safely, undisturbed, and perfectly able to carry out the same experiments that humans can. That begs the question, why not just send more machines?
We have already begun to operate robots on the surface of the Earth from the International Space Station. When we build the Deep Space Gateway around the Moon, we will be operating lunar rovers and vehicles across the surface of the Moon from that orbiting facility, much as we do from the space station today. Robots are playing a vital role in preparing the way for humans. But there's something implicit within human nature that requires us to walk to the hill and look beyond, to look to the next hill and go to that one. It is part of curiosity. It is part of the very essence of what it is to be human.
The voyage to Mars is humanity's greatest space exploration endeavor yet. But the path forward for humans is fraught with danger and uncertainty.